You've probably heard quantum physics described as the science of things being weird, or the study of tiny particles that act random for no reason. That's not exactly wrong. It's also not really an answer. Quantum physics is what happened when, around the turn of the 20th century, physicists ran their best equations on the smallest scales of reality and got answers that made no sense. Not hard to calculate, no sense, but the math says energy comes in indivisible chunks and a particle can be in two places at once. No sense. And instead of throwing the math out, they kept it, because it kept being right. Every single time. By the end of this video, you'll understand where quantum physics actually came from, the handful of experiments that forced it into existence whether physicists wanted it or not, the ideas, superposition, entanglement, uncertainty, that everyone's heard of and almost nobody has heard explained correctly, and where all of this ends up. Not in a physics classroom, but in your phone, your GPS, the sun over your head right now, and the computers being built to replace the ones you're watching this on. Let's start with the crisis that made quantum physics necessary in the first place, because nobody set out to invent it. It got dragged into existence by a math problem nobody could solve. In the final years of the 1800s, physicists were trying to describe something that sounds almost boringly simple: how hot objects glow. Heat something up, a piece of metal, a star, a light bulb filament, and it radiates energy across a spread of colors that shifts as the temperature climbs, from dull red toward white hot. Classical physics, the physics of Newton and Maxwell that had explained essentially everything for 2 centuries, had a formula for predicting exactly how much energy should radiate at each color. And that formula worked beautifully, right up until it predicted that a warm object should radiate infinite energy at the ultraviolet end of the spectrum. Not a lot of energy. Infinite. Physicists called this the ultraviolet catastrophe, because that's exactly what it was. A sign that a 200-year-old framework had hit a wall it couldn't explain its way past. In 1900, a German physicist named Max Planck found a fix, but he didn't love it. Planck proposed that energy isn't radiated smoothly, the way you'd pour water from a jug. It's radiated in discrete, indivisible packets, which he called quanta, from the Latin word for how much. Do the math with energy chopped into these fixed-sized chunks instead of treated as continuous, and the infinite catastrophe vanishes. The formula matches reality perfectly. Planck himself reportedly considered it a mathematical trick to patch a broken equation, not a description of how the universe actually works. He was about to be proven wrong about that in the most consequential way imaginable. 5 years later, in 1905, Albert Einstein took Planck's trick and did something Planck hadn't dared to. He said it was real. Einstein used the idea of energy quanta to explain something called the photoelectric effect, the strange fact that shining light on certain metals kicks electrons loose, but only if the light is a high enough frequency, no matter how bright you make it. Dim ultraviolet light knocks electrons free instantly. Blindingly bright red light does nothing at all. That result made no sense if light was a smooth, continuous wave, which is what physicists had settled on believing for the better part of a century. It made perfect sense if light itself arrives in discrete particle-like packets, what we now call photons, each one carrying a fixed amount of energy tied to its frequency. Here's a detail worth sitting with. When Einstein won the Nobel Prize in 1921, it wasn't for relativity, the theory most people associate with his name. It was for this, for showing that light, the thing physicists thought they'd fully explained as a wave, was also, somehow, made of particles. Light behaving like both a wave and a stream of particles at the same time. Sit with that, because it's about to get worse. In 1913, the Danish physicist Niels Bohr used quantized energy to explain something else classical physics couldn't touch: why atoms don't collapse, and why heated elements glow in very specific, distinct colors instead of a smooth rainbow. Bohr proposed that electrons don't orbit an atom's nucleus at just any distance. They can only exist in specific fixed energy levels, like rungs on a ladder, and they jump between rungs by absorbing or releasing energy in exact quantum-sized amounts. This is actually where the phrase quantum leap comes from, and it's worth pausing on, because pop culture has the meaning almost exactly backward. A quantum leap isn't a huge dramatic change. It's the smallest possible jump physics allows, an electron moving from one fixed rung to the very next one, with nothing in between. Somewhere along the way, marketing took the smallest jump in physics and turned it into a synonym for a giant one. Then, in 1924, a French physicist named Louis de Broglie flipped the whole problem around and asked an unsettling question. If light, which everyone had always assumed was a wave, could act like a particle, could matter, which everyone assumed was made of solid particles, act like a wave too? He proposed that electrons, and in principle any piece of matter, carry an associated wavelength. It sounded like speculation. It wasn't. 3 years later, in 1927, American physicists Clinton Davison and Lester Germer fired electrons at a crystal and watched them produce an interference pattern, the unmistakable fingerprint of a wave, something a stream of solid little particles has no business doing. This is the point where wave-particle duality stops being a phrase you've heard and starts being something you can actually picture, because there's one experiment that makes the whole idea impossible to unsee. Take a barrier with two narrow slits cut into it and fire something at it, say electrons one at a time, with long gaps in between so there's no possible way they're interacting with each other. Common sense says each electron goes through one slit or the other and lands directly behind it, building up two clean stripes on the detector screen behind the barrier over time. That is not what happens. What actually builds up, one lonely electron at a time, is a full interference pattern, the same stripe pattern you'd get from two overlapping water waves, as if each individual electron passed through both slits at once and interfered with itself. This exact result was demonstrated with unmistakable clarity by Japanese physicist Akira Tonomura and his team in 1989, firing electrons one at a time and recording, on video, the interference pattern slowly assembling itself dot by dot. Nobody has ever produced a version of this experiment where a single particle, unobserved, behaves like a simple little ball going through one slit. The particle behaves as though it explores every path available to it simultaneously, a state physicists call superposition, right up until it's measured, at which point it commits to one outcome. Which brings us to the misconception that trips up more people than any other idea in this entire field, so let's kill it properly. The idea that a particle only chooses once a conscious human looks at it, as if your attention is somehow reaching into the experiment and forcing reality to pick a side. It's an understandable mix-up because the word physicists actually use is observation, and in plain English that word implies eyes, a mind, someone paying attention. But in quantum physics, observation just means any interaction that forces a quantum system to interact with its surroundings in a way that pins down a definite outcome. A detector clicking, a photon bouncing off a screen, a single atom brushing against another. No consciousness required. No physicist, watching or not watching, changes the outcome by wanting to. A machine that nobody ever checks the readout of produces exactly the same collapse as a lab full of scientists staring at a monitor. This particular misconception has a name in physics circles, the observer effect, sometimes tied to something called the von Neumann-Wigner interpretation. And while a handful of physicists have taken it seriously as genuine speculation over the decades, the overwhelming mainstream view is that it's simply wrong as an explanation for what's happening. However often it gets repeated in documentaries, because it makes for better television than a detector interacted with a particle. If the idea that reality doesn't fully commit to an outcome until something forces it to, is the kind of thing that's genuinely rearranging how you think about, well, everything alike, helps a video like this find more people who'd get just as into this as you clearly are right now. Because the next idea is the one that made even the physicists who discovered it deeply uncomfortable. In 1927, The German physicist Werner Heisenberg formalized something that follows directly from all of this: the uncertainty principle. It states that there's a fundamental limit to how precisely you can simultaneously know certain pairs of properties about a particle, most famously, its exact position and its exact momentum. The more precisely you pin down where a particle is, the less precisely you can possibly know how fast it's moving, and vice versa, no matter how good your instruments are. This is worth a correction of its own, because it gets mangled almost as often as the observer effect. This isn't a statement about clumsy measuring equipment jostling a delicate particle around. Even with a hypothetically perfect instrument that touched nothing and disturbed nothing, the uncertainty would still exist, because position and momentum aren't both simultaneously well-defined properties of a quantum particle in the first place. It's not that we can't know, it's that in a very real sense, there isn't a precise answer sitting there waiting to be found. The universe was never as solid as it looks. That's the idea sitting underneath every single discovery in this field, from Planck's reluctant quanta to a single electron interfering with itself. Keep it in your back pocket, because it's about to get stress tested even harder. In 1935, the Austrian physicist Erwin Schrödinger, the same Schrödinger whose wave equation, published in 1926, is the mathematical engine that actually predicts how quantum systems evolve over time, proposed a thought experiment specifically designed to make this whole framework sound ridiculous. Seal a cat in a box with a radioactive atom that has a 50% chance of decaying within an hour, wired to a mechanism that releases poison gas if it does. According to a strict reading of quantum superposition, until you open the box and check, the atom exists in a superposition of decayed and not decayed, which would mean the cat exists in a superposition of dead and alive at the same time until observed. Here's the misconception worth correcting directly, because Schrödinger's cat gets treated as proof that quantum physics really does say a cat can be alive and dead simultaneously. Schrödinger proposed this specifically as a criticism, to highlight what he saw as an absurd consequence of applying quantum rules naively to large, everyday objects. He wasn't arguing the cat really is in two states at once. He was arguing that if you think it is, you've misunderstood something about where quantum effects stop applying, and ordinary classical reality takes back over. A boundary physicists still debate the precise nature of today, nearly a century later. The thought experiment survives not because it proves cats can be undead, but because it's a genuinely brilliant illustration of exactly where our intuitions and the quantum math stop agreeing. That same year, 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper trying to poke an entirely different hole in quantum theory, and in doing so accidentally described one of its strangest real features. If two particles interact and then separate, quantum physics predicts they can remain correlated no matter how far apart they travel. Measure a property of one, and the corresponding property of the other is instantly determined, even if it's now light years away. Einstein thought this was so implausible, it had to reveal quantum theory was incomplete, dismissively describing the whole idea as spooky action at a distance. He intended it as a takedown. It wasn't one. This phenomenon, now called quantum entanglement, is real, and it's been confirmed experimentally more times and more rigorously than almost any other result in physics. In 1964, the physicist John Stuart Bell worked out a mathematical test, now called Bell's theorem, that could actually distinguish between genuine quantum entanglement and any classical explanation involving particles secretly carrying hidden, predetermined instructions the whole time. Starting with French physicist Alain Aspect's experiments in 1982, and refined by many teams since, including work that eventually earned Aspect, John Clauser, and Anton Zeilinger the 2022 Nobel Prize in Physics, every serious test of Bell's theorem has come back the same way. Entanglement is real, and it isn't secretly classical information hiding under the hood. Einstein's attempted takedown became one of the most thoroughly confirmed results in the field he was trying to poke a hole in, which sets up misconception number 3. And this one matters because it gets used to justify all sorts of nonsense. Entanglement does not let you send information faster than light. If you measure your half of an entangled pair, you get a genuinely random result. And your partner, measuring their half however far away, gets a correlated but equally random result. But neither of you can control what you get, so neither of you can encode a message in it. The correlation only becomes useful, or even provable, once someone physically compares both results side by side, which requires sending that comparison through completely ordinary, light speed or slower channels. No telepathy, no instant communication across the galaxy, just a correlation that's real, verified, and still respects the speed limit everything else in the universe has to obey. All of which raises an obvious question. If quantum physics is this strange, why doesn't your coffee cup do any of this? Why don't you flicker in and out of existence on your way to work? The honest answer is that quantum effects don't vanish for large objects. They just wash out almost instantly through a process called decoherence, where a quantum system's fragile superposition gets scrambled by countless random interactions with its environment. The air around it, the light bouncing off it, its own internal jostling atoms. A single isolated electron can stay in superposition for a meaningful stretch of time. A cat, or a coffee cup, made of roughly a mind-melting number of interacting particles, decoheres into ordinary, boringly classical behavior, so fast it might as well be instant. This is genuinely one of the more active areas of modern quantum research, figuring out exactly where the line sits and how to hold quantum behavior together in larger and larger systems for longer and longer, which finally is where this stops being abstract. Quantum physics isn't a museum piece from the 1920s. It's running underneath your life right now. Every transistor in every computer chip depends on quantum tunneling and quantum behavior in semiconductors to function at all. Lasers, in your fiber optic internet connection, in the barcode scanner at a grocery store, work because of quantum transitions between atomic energy levels, the same rungs on the same ladder Bohr described in 1913. MRI machines read the quantum spin states of atoms in your body to build an image of your insides without cutting you open. Even GPS, the thing your phone uses to find you, needs quantum-informed corrections to keep its atomic clocks accurate enough to be useful. And right now, physicists and engineers are trying to push quantum weirdness itself into a tool, in the form of quantum computing. A normal computer bit is either a 0 or a 1. A quantum bit, or qubit, can exist in a superposition of both at once, and qubits can be entangled with each other, letting a quantum computer explore an enormous number of possible solutions simultaneously, in a way a classical computer has to check one at a time. In 2019, Google announced that its Sycamore processor had completed a specific calculation faster than the world's best supercomputer could, a claimed milestone the industry calls quantum supremacy, though the exact scale of that advantage and how meaningfully it translates to solving real-world problems is still genuinely debated among researchers. The practical significance of the 2019 quantum supremacy claim remains disputed within the field. These machines won't replace the laptop you're watching this on. What they might eventually do is solve specific categories of problem: drug molecule simulation, certain kinds of encryption, materials science, that are effectively impossible for any classical computer, no matter how large, to brute force through. The universe was never as solid as it looks. A century ago, that sentence was a strange philosophical implication buried in some intimidating equations. Today, it's the operating principle behind the phone in your pocket, and possibly the operating principle behind the computer that eventually simulates a new medicine your body needs. If you want more of these, ideas that sound like abstract physics trivia, until you realize they're quietly running your entire day, hit subscribe, drop a like if this rewired anything for you, and tell me in the comments which part of this broke your brain the hardest. One last thing, and it's arguably the single most consequential piece of quantum physics nobody ever puts in the headline. You're only alive right now because of quantum tunneling. Deep in the sun's core, hydrogen nuclei fuse into helium to produce the light and heat that reaches Earth. But by the classical rules of electromagnetism, those positively charged nuclei should repel each other far too strongly to ever get close enough to fuse, even at the sun's staggering core temperature. Quantum tunneling is the only reason fusion happens at all. Particles have a genuine, non-zero probability of simply appearing on the other side of an energy barrier they classically shouldn't be able to cross, as though they briefly borrowed a shortcut the rest of physics doesn't allow. Without that one quantum loophole, stars as we know them wouldn't shine, and neither would you be here to watch this sentence end.